and hello everybody. Welcome to the Single Piles webinar. I'm going to start today with the objectives, and the purpose of this webinar really is to help you appreciate the theory and the theory of how single piles can be analyzed, to understand which Oasis programs are available for this kind of analysis. And some of this theory may be familiar to you, but it's necessary to understand to appreciate the analysis methodology and understand what goes on under the bonnet for the different programs. And we're also going to help you further understand how the software is applied in industry through case studies. So this webinar really focuses on single piles, but other webinars do cover subjects in the same area, and seeing that we're only covering mainly the methodology here, you can refer to other webinars on how to set up models in AdSec, Pile and Alp, how to analyze piles as part of an embedded retaining wall, and analyzing pile groups. I've given links to these at the end of the presentation, and you can have a look at that later. So, firstly, what is a single pile? Well, a single pile is a pile that, when loaded, does not have any interaction effects with the adjacent piles, and the spacing between the piles often depends on the solution modeled and the ground conditions. But typically, for example, if you consider vertically loaded piles, the spacing is more than 3 times the diameter of the pile. If you consider maybe, for example, the settlement effects and you're looking at a settlement calculation, the pile spacing is typically more than 10 times the diameter of the pile. But alternatively, if you're looking at laterally loaded piles, the spacing really depends on the loading direction with respect to other piles. So as I mentioned here, it really depends on the kind of analysis you're doing, the kind of piles you have, and everything else, and this should be considered before you start the analysis. What Oasis software can be used to analyze single piles? Well, there are 3 main programs. The first is Pile, which calculates the vertical pile capacity and the settlement. Now, the settlement side of Pile is actually an incorporation of a program that was previously called PILSET. So PILSET has been put into Pile with exactly the same functionality. And this gives you design outputs such as required length and pile settlement. We've also got Alp, and Alp gives you the behavior of the pile under lateral loads. And for example, it gives you as a design output moments and cage lengths. And there's AdSec, which analyzes a section of the pile, and it carries out a nonlinear concrete and composite section analysis. So this gives stiffnesses and cracking. So, to start with, how would you calculate the capacity and settlement of a pile? Well, you could use Oasys Pile. And Oasys Pile can calculate the capacity, and it incorporates a settlement calculation as well. But they are based on 2 different types of methodology and 2 different types of theory. So in terms of discussing the theory, I'm going to deal with them separately. So we'll start with pile capacity. What does Pile do to calculate pile capacity? Well, it determines the vertical load capacity for a pile for different pile types. And when you say different pile types, I mean, for example, square-driven piles, steel H-section piles, different pile materials as well, such as steel, precast or cast in situ piles, range of pile lengths, different soil layers, site-specific groundwater conditions, which can be either phreatic or piezometric, and different factors of safety or design resistance. So we'll touch upon all of this now. Why use Pile? Why was it developed? Well, it replaces the need for spreadsheet calculations and errors that might be within them. Also, with Pile, the graphical interface is very powerful, and it makes checking very easy, and it helps you check the outputs of other engineers as well. It enables you to calculate the shaft and base capacity for a total stress problem with undrained parameters, an effective stress problem with drain parameters, or a combination of both, something like sands overlying clays or vice versa. It can model more complex tubular or hollow piles because it models the plugged and unplugged behavior where the soil sticks to the inside of the other piles. And it can also incorporate negative skin friction. So I'm going to touch upon the theory here. if you do want any of the theory in more detail for any of the programs, I suggest you just have a quick look at the manuals as well if you're not sure about anything. But to start with, if we look at the pile capacity and the shaft capacity theory, for the total stress, the friction is a function of alpha and Cu. But for the effective stress, there are two methods of calculation. You can take the earth pressure method, which relates shaft friction, where shaft friction is related to horizontal effective stress and the soil pile friction angle. Or you could use the beta method, where shaft friction is related to vertical effective stress. Now, the horizontal and vertical effective stresses can actually be calculated by the program, or you can input it as the user. So it gives you that functionality. For the end bearing, if we look at the total stress, the base capacity is given by NC times Cu. Now, NC actually depends on the pile type, but the program can calculate NC based on the pile dimensions you give it, so that's quite handy. For the effective stress calculation, the base capacity is NQ times the vertical effective stress. And as you can see here, there are a number of ways of calculating NQ. And I think the manual gives in more detail, for example, the Bolton method, for example, or if you wanted to input in yourself NQ and thigh curves, it will give you guidance on that. In terms of the ultimate capacity, and when I say ultimate capacity, I mean the capacity before factoring. For solid piles, it's fairly simple. It's really the shaft and base capacity minus the negative skin friction. But for hollow piles, there are actually a number of options. So the capacity is calculated, for example, for a plugged case and an unplugged case, and so on and so forth. And the program takes a minimum of these. Well, what happens when you start factoring the values? Well, for allowable capacity or working load, the factors are specified by the user through partial and global factors, and these are used in various equations. Now, the 4 equations are listed here, and it gives you the working load. And the minimum of these equations is the allowable capacity. So based on the factors you put in, it will calculate values of PD 4 times and take the minimum. Also, the limit state approach is incorporated, and again, this depends on the user to input the shaft resistance and the base resistance, and on the basis of that, it'll calculate your design resistance. So if we look now at a quick summary, as you can see, Pile outputs the ultimate and allowable capacities and the tension and compression capacities based on inputs such as pile section, underreams, and soil parameters. But just to help you digest all this, the best thing for me to do would be to show you a pile file. So we'll start off with the analysis options. And as you can see here, you have the option here of capacity or settlement, or both, so you can tick both on. But for the purposes of showing you how the capacity calculation works, I've ticked capacity only. We've got the pile properties in here, and this is interesting because, as you can see, there are a number of options of piles: solid circular, solid square, hollow circular, hollow square, and H piles. You've got with or without underream. As opposed to just considering one single pile length, it'll consider a range of lengths, a minimum and a maximum, so you can look at your values at different levels, and that's quite helpful. And also, beyond that, you can choose more than one pile diameter. So for example, if you're taking some pile capacity charts, if you're looking at structural loads and trying to decide what kind of piles you'll use, this kind of thing is pretty helpful, and that's also available in Pile. So if we go straight to the graphical output, I'll start with the input parameters, and as you can see here, you've got a minimum length and a maximum length of the pile, and the range is shown with the dotted line. And right at the top, you can see a cross section of the pile. It's showing a 0.6 meter cross section here. But if I press the plus button, it goes up to 0.7 meters, and I'll show you how this affects the results just in a moment. But if you look at your left-hand side on Pile, these are all input parameters that I'm clicking on. So as you can see the unit shaft friction, the under cohesion, the pore water pressure, the vertical effective stress, and the horizontal effective stress. And this is helpful because it helps you understand your inputs and see that your inputs are as you would expect them to be. But if we go to the output, say if I had put a hollow pile in, just for interest's sake, you can actually get the plug capacity, the unplug capacity, and so on and so forth, and the internal skin friction. But I've just chosen a standard CFA pile. So we've got the total skin friction here and the end bearing capacity. So they come out on the right hand side because they're your outputs. And if we click that off, we can get, for example, the working load and the ultimate load. This is in compression, and again, we can get it in tension. So that gives you an idea of what's going on. And if, say, for example, I'm at 0.6 meter diameter here, if I press the plus button, you can see the change in results and the reduction as you will expect as you increase the diameter to 0.7 meters. So that gives you a good idea of what's going on there. I'll just go back to the presentation. So now that we've covered the settlement calculation, now that we've covered the capacity calculation, how do you carry out a settlement analysis in Pile? Now, the Pile settlement analysis uses a different theory, and it's based on a paper by Matson-Poulos. The analysis uses a purely elastic model, and it uses the Young's modulus of the soil above the toe, the soil below the toe, and the Young's modulus of the pile itself. And what it basically does is that it looks at a compressible pile in sections, and it deals with a continuum soil. So if we look at this in a little bit more detail, on your right hand side is a little square, a rectangle representing a segment of the pile. And what's happening here is that the stress on a segment of a pile from above is reduced by the shaft friction along the side of the pile. So the pile stress behavior is solved using a finite difference method as you go down the pile, or simply it's really a vertical equilibrium problem. So that's how the pile is dealt with. If we think about the soil behavior, I mentioned that it's a continuum model, so it's an integration of Mindlin's equations. And for the soil pile interface, we get compatibility unless limiting skin friction is exceeded. So, in summary, the settlement aspect of Pile outputs the pile settlement, the soil settlement away from the piles, and the pile stresses. And this is based on inputs such as pile dimensions, soil stiffnesses, and negative skin friction and heave. So with everything we've discussed, and having a look at theory for settlement, it would be really good for you to go into the program and understand how it works. So if I just go into Pile, we'll start off with the analysis options. As you can see here, I've ticked the settlement section, not the capacity. And as you can see, we've input factors such as Young's modulus and Poisson's ratio. If I go to the output of Pile, we've got the limiting shaft skin friction and the actual shaft skin friction. And as you can see, what's happening there. Again, I've got two cross sections, so I can look at the difference between a 0.6 mil and a 0.7 mil. Sorry, a 600 mil and a 700 mil CFA pile. We've got the pile stress, and we've got, as well as this pile displacement, you can actually find the soil displacement at a certain radius away from the pile. So say I've got a 600 mil diameter pile here. If I maybe go 0.4 meters from the central radius, I can have a look at the behavior of the pile and the settlement, and also what's happening with the limiting shaft skin friction and the pile stress. But as well as just looking at two different cross sections of piles, so instead of, for example, just comparing 600 mil and 700 mil, the settlement calculation goes further than that, and you can actually look at the difference it makes by reducing the length of your pile. And as you can see, the value is actually appropriately changing. So it really helps you understand how your pile is behaving according to settlement, and it's very helpful that way. So I'm now just going to move back into the presentation. I've demonstrated Pile. We have now discussed the capacity and settlement calculations for single piles. So we've just had a quick look at that. How do we look at the behavior of a single pile under lateral load? So Alp calculates the earth pressures, the horizontal movements, the bending moments, and shear forces for a pile. and it's based on the lateral loads, moments, and displacements. So, for example, soil movements from Siren could be used to see how the pile copes under seismic loads. So that'll give you that's an input of displacements, and you can see the behavior of the pile under seismic loads. You can also input lateral and rotational restraints, and you can look at the soil load deflection behavior. Now, the theory behind, or the representation of ALP, is such that ALP determines the internal forces developed along the pile due to lateral loads or displacements. And as you can see with this model here, it models the pile as a series of elastic beam elements. It models the soil as a series of non-interactive, non-linear springs. The forces, moments, and stiffnesses are applied at nodes, and the soil response is modeled as either elastic plastic or PY. So two soil models are available, and we'll start with the elastic plastic model. The elastic plastic model assumes elastic behavior until passive limit is reached. So it's quite simplistic for a soil. Once a passive limit is reached, ALP applies a constant pressure on the pile and the load moves further down the pile. So initially, before the passive limit is reached, we need to know our K value or initial stiffness, and this is calculated using Young's modulus and E factorial. And E factor can be got from Bromson-Poulos or Tomlinson, and the method is given in the manual. For the passive limiting force, that's calculated using KQ or KP, and these can be calculated in the program or by using graphs in Tomlinson. So the KQ value, for example, the passive resistance coefficient for the frictional component of the soil, or the KC value, the passive resistance coefficient for the cohesive component of the soil, can actually be got from Tomlinson or calculated within the program. But, and as I mentioned, it's the elastic plastic model is not as realistic as we would like, and a more realistic model would be the PY soil model. So ALP has predefined models for soft clay, stiff clay, sand, weak rock, and strong rock. And also based on empirical values that you might have yourself, the user can define PY curves for the different strata. So this can actually easily be selected from a drop-down menu of materials or predefined materials in the gateway section. And that's something that the user can do. Also, ALP considers cyclic loading. And cyclic loading is very useful, for example, if you're considering a wind turbine on a single pile. So you might have swaying to and fro, and that would account for that kind of problem. Now, how do you deal with loads, displacements, and restraints in ALP? Well, the lateral loads and moments can be applied at any node. Soil displacements from another program or field data can be applied down the pile. Restraints can be applied at any node and be either a moment or a lateral restraint. And loads and displacements can be applied in increments of the total value. So all the values I've mentioned and discussed with ALP, as well as the stiffness or the EI value, go into a stiffness matrix, and ALP calculates the answer. Now, the answer can be in the form of a tabular output, which can be exported into Excel for further interrogation. And in this tabular output, each increment of, say, for example, load is listed. It's also very easy to check the results in ALP and see that you're getting something realistic out using the graphical outputs. And also, the bending moments and shear forces, which are outputted from ALP, can be used in the reinforcement design. And that neatly brings me on to AdSec. Now, AdSec is a program which does a nonlinear concrete and composite section analysis. It can handle a number of different types of sections, not just plain piles, as you can see here. And it handles sections which are a mix of, for example, a composite section, which is concrete and it's got reinforcement in, so it's very useful for piles. How does AdSec work? What's the theory behind it? Well, the program carries out a strain plane analysis for any given section to solve the following strain equation. So it looks at a plane and it calculates the strain for it, basically, and it solves the strain equation. For the ultimate limit state analysis, AdSec gives you the ultimate strength of the section, and it uses material factors or strength reduction factors from various codes such as EC2, for example. For the serviceability limit state analysis or SLS analysis, you're looking at the section in its normal working state. So you allow for both long-term and short-term loading. So for example, it can consider creep. So AdSec, in summary, outputs values such as section capacities, section stiffnesses, and cracking. So for example, if you've got a section stiffness or the reduced stiffness and EI values, you can actually feed that back into a program like Alp, and the cracking values, of course, are useful to see how your pile is performing. And this is based on inputs such as the section, reinforcement, and loads. So I'm just going to touch upon some outputs in AdSec here, and then we'll go into the program. So as you can see, the load case can be plotted, and in this particular section capacity and M chart, you can see that the load cases are within your envelope and your design is okay. Again, you've got the moment interaction here, and you can see where the load cases fit into that, and the different axial loads, and you've got your serviceability graphs, so you can look at what EI values you should be taking and putting back into a program like Alp. So if I just go into AdSec, so you can see here's one I've done earlier. It's just a simple pile. So if I double click on this, you can see pretty much how it's done. It's a very quick and easy thing to do. You just say that it's 600mm diameter. You can either add special bars, maybe LIDAR bars, or pre-stressed bars, and alternatively you can just do what I did, put a quick template in. I put a bit of cover in there, or you can follow the code cover. I've said there's 12 bars in a ring, and I've given them each diameter. So that's what I've done. How do you go about analyzing it? Well, first put your loads in. So, let's see. So this will give me my ultimate load. So say 1500 load, and in the analysis case, you've just got to put your analysis case in. So your ULS case is your unfactored loads, and your SLS case is a factoring of that load, so 0.75 of the load. Okay, so if I go, for example, and look at my interaction chart, if I go and I can actually plot my load points in there. Okay, and as you can see, it's well within limits. Excellent, great. Maybe I want to have a look at the cracking. Okay, and as you can see down here, we've got crack widths. So I'm getting a crack width at the surface of less than 0.1 mil. So that's excellent again, should be okay. And if I go in, I can actually see where cracking might be occurring by just displaying it here. And as you can see, these bars are more prone to cracking. So it gives me a good idea of how my particular pile is performing, and in that way it's very useful. So in summary, AdSec gives you the ultimate and serviceability condition checks. It deals with regular and irregular concrete and composite sections. It can calculate nonlinear crack section stiffnesses and capacities and crack widths. And also I'm going to cover AdSec in one of our case studies as well and show you how it's used. So that nicely moves me on to the case study section. So you must be thinking that was a lot of theory there. But it would be nice to see how these programs are used and how industry is using them. So I'm going to start off with a case study from one of our external customers. I'd really like to thank Bernd Luby for this case study, and it's the design of it's a pile design for transverse loads by Bernd Luby and partners for McCarthy's level crossing near Kilmarnock. So Bernd Luby were asked to design the pile foundations for the proposed replacement of the McCarthy's level crossing. the piles had to resist a 830 kilonewton maximum uniaxial compressive load, and no tension or moment loads were to be transferred to the piles. So the piles were subjected to 175 kilonewton horizontal load per pile from the superstructure, and there was also rotational stiffness from the pile cap of 175 kilonewton meters per rate. So for the proposed solution, all the piles are designed to be bearing in the stiff to very stiff boulder clay, and this was conservatively ignoring the upper 2.5 meters of overburden. And the consulting engineers specified to Bernd Luby that the piles should be a minimum of 600 mil in diameter. So now we'll go into the analysis and see how Bernd Luby dealt with the transverse load first. Bernd Luby used Alp to analyze the transverse load, and for the Alp analysis, a rotational stiffness had been taken from the pile cap. All the piles are to be fully tied into the pile cap, so as you can see, the rotational stiffness there is around 50,000. And from the outputs, and this is a complete Alp output, you can see from the pink line, the maximum pile shear force was 175 kilonewtons. From the red line, the predicted movement or head movement is around 10 mil, which is good. And also you've got a maximum pile bending moment of 145 kilonewton meters. And if you just look as you go down the pile, if you look at what's going on at around minus 6.5 meters, as you can see, the values are coming right down there. So the pile reinforcement should be installed to a minimum depth of 6.5 meters below the pile cutoff level, as per the Alp output. So Bernd Luby also used AdSec to analyze the structural capacity of the pile. The pile reinforcement capacity came out with this NM graph, as you can see, this load and moment graph. And if we zoom into it, you can see that Bernd Luby has looked closely into the AdSec output, and for the compressive load, as previously mentioned, at 830 kilonewtons, the allowable bending moments coming out at around 280 kilonewton meters. So how does this fit in with the actual moment that's occurring from our Alp output? Well, our design bending moment is the generated bending moment times a factor of safety. Bernd Luby took the factor of safety to be 1.5, and their generated bending moment from Alp was 145 kilonewton meters, so that was on the previous slide. So actually their design bending moment is 218 kilonewton meters, which is less than the 280 kilonewton meter given by AdSec as our allowable bending moment. So the design is okay. That really helps you understand how AdSec and Alp are used in conjunction. Now I'm going to touch upon this case study. It's available on the internet in detail, but it looks at how the whole piling suite can be used together, that is AdSec, Pile, Alp, and also Fru, to design a retaining wall in more complex conditions. So for the UCL hospital and the construction of the UCL hospital, there were actually a lot of geotechnical constraints. And for the design of the basement retaining wall, the section of the retaining wall running alongside the Rain Institute had several restrictions. One was the actual proximity, physically, to the Rain Institute. They were working in central London. It was very close anyway, but the Rain Institute was less than a meter away from the retaining wall, so it's very close. And the Rain Institute piles would also be affected in that way. And due to the requirement to locate a service lift, there are tight space restrictions that affect the actual wall thickness as well. So the Arup engineers proposed to construct a 600 mm diameter hard soft board secant pile wall with male piles at 750 mm diameter centers, and a smaller pile diameter of 600 mm in this area was required, but the wall had to be temporarily propped at 2 levels for that reason. So how did they go about analyzing it? Well, actually, what they did was, seeing that movements were so sensitive in this case, and due to the proximity of the Rain Institute, accurate modeling really was essential. So what they did was they started with an initial pass by modeling the retaining wall construction in Fru, and out of their model, they got horizontal ground movements and vertical stresses. The horizontal ground movements were fed into Alp, and the vertical stresses were fed into Pile to look at how the Pile was performing. And on the basis of this, axial stresses were fed into AdSec, and the moments from Alp. So if you think about the plot, the moments from Alp were fed into AdSec. But then an iterative process had to be taken up between AdSec and Alp to get a better design. So what happened was that the cracked EI from AdSec was fed back into Alp, and so on and so forth. And the Arab engineers actually commented that each of these programs actually deals with a different design methodology. So it's important that they're separate, but at the same time, there's a lot of compatibility because of the gateway interface and the way that they can be used together, copying and pasting between programs, and so on and so forth, such that it actually made it very easy and very quick to run this analysis and get to a final solution quickly. So as you can see, here's an output. This shows the settlement, pile settlement analysis. And as you can see, we've got the limiting shaft skin friction, the shaft skin friction, the pile stress, and pile displacement. So that's all there. So in summary, just to touch upon everything that we've covered, today I've discussed the theory and the application of programs to analyze single piles. We've also shown how it can be applied through case studies and gone into the interface and just introduced you to the different interfaces. So for Pile, it calculates the pile vertical capacity and settlement analysis, and the design outputs a required length and pile settlement. For Alp, the program calculates pile lateral loads, and you get outputs such as moment and cage length. And outputs such as moment, for example, feed into programs like AdSec, where you get the nonlinear concrete and composite section analysis, and you get values such as stiffness and cracking. So as this was just an introduction to theory, an introduction to the programs, it would be helpful for you to go back and have a look at the manual, try the step-by-step examples, and if you actually don't have the software, download the trial version and try it. Watch the online tutorials and the webinar recordings because they will familiarize you with the way the programs are set up, running through the programs, and so on and so forth. And we would really like to hear from you. Pop us an email if you have any questions. Feel free to call us. We're always at the end of the phone. And also, I've included here some helpful links. A recording of this webinar would be made available on the internet, and a PDF of this webinar will also be made available, so you can look at these links at your leisure, maybe a week from now. So it just goes for me to say thank you very much for your time. I hope it's been useful, and are there any questions?